Okay, good evening. This is Professor David De Los Reyes. Okay, the date is September 21, 2023. The time is 11:05 p.m. Okay, my topic for tonight will be a long video format discussion on the subject matter AC machines, and I am now, and we are now also at lesson number 18. Okay, let's proceed. Subject matter for tonight will be AC machines, lesson number 18. The title of the topic is Formulas under Open Circuit Test. I will try to bring out the so-called derivation of the formulas needed in the so-called computation of the total core loss of a transformer. Because the last time around, I brought out the equations on how to compute the copper loss, the winding loss. For now, I will be bringing out the formula on how to compute the total core loss. And there are actually two components. Okay, let's proceed. For the core loss, there are two components. It's the hysteresis and the eddy current loss. This has nothing to do with the winding of the transformer. This will now, core loss meaning it's the loss referred to the loss of the core in which the windings are wound, right? There are losses on those, and they are termed to as hysteresis and eddy current. The hysteresis loss is just actually the loss due to the so-called current reversal. Due to the reversal of the alternating current, back and forth, there is a loss with it, and that is termed to as the so-called hysteresis loss. It was discovered by engineers that the current reversal, on the core will present a hysteresis loss, and the name that loss to be the so-called hysteresis loss. So for hysteresis loss, this is the loss due to the so-called current reversal. The other loss is actually the eddy current. And eddy current, in layman's language, it's the loss due to the interaction of the current and magnetic flux. If there is a current passing through the winding, there should be a flux that will come out. And the interaction between the two is termed to as the so-called eddy current loss. There's a loss for that one, and engineers discovered it and they named it as eddy current loss. Okay, I will try to bring out the formulas for taking the value of hysteresis loss and eddy current loss. Actually, these formulas are actually derived by the engineers performing experiments on the open circuit test. Okay, and for the derivation of this one, they were the ones who discovered these formulas, right? So capital letter P with the subscript H, meaning the total hysteresis loss, is actually equal to capital letter K with the subscript H. So all the subscripts refer to hysteresis, right? Hysteresis loss is equal to K sub H. It should be a constant that is referred to under hysteresis loss times frequency times capital letter B with the subscript M raised to 1.6. Okay? I don't know how they were able to arrive at this 1.6 here, but the engineers before performed an experiment on how to compute this hysteresis loss. So I will repeat it. PH will be KH times frequency times the flux density. Flux density, capital letter B with the subscript N is a mutual flux density raised to 1.6, and the unit of this should be watts. Right? Supposed to be for this to be watts, frequency will be in hertz, and flux density will be in Maxwell's per square inches. So actually, I think I got it here. Flux density is designated by capital letter M. Am I still on camera? Flux density, and the unit is actually Maxwell's per square inches. Maxwell is a family name of the inventor of the so-called, not inventor, the one who discovered flux density, right? Okay, formula number 2 for the eddy current loss. Okay, capital letter P with the subscript E, because P under the standard of AC machines is actually true power, right? The unit is actually watts. So P with the subscript E, this is subscript E again. So this E here refers to eddy current, E. This H here refers to hysteresis. So capital letter P with the subscript E should be equal to K with the subscript E times the square of the frequency square, okay, multiplied by the flux density quantity square. There's a difference on equation number 1 and number 2. They're different, okay? So during the experiment, okay, they came out with these equations here, PH and PE, and the right hand side is actually in terms of frequency and flux density, and so the right hand side for the eddy current. But the variations is different. This is raised to the 1.6, this is a square, and this is a square. I don't know why it was a frequency square and b sub m square. So we accept it as it is. We assume it is correct. So the starting point of the derivation of the formula will start here. Okay. Okay, let's try to derive the final formula and how to compute hysteresis loss and eddy current loss. Okay. From the equation E equal to the equation for the induced voltage for the transformer. It's 4.4. We passed by this one. Actually, I've given you the derivation of this. E is actually 4.44 times frequency times number of turns times mutual flux times 10 to the minus 8, and this is actually in volts. Right? We passed by this one. This is induced voltage. Right? Let's try to compute for the mutual flux. So mutual flux will be E times 10 to the 8 over 4.44 times frequency times N. We call this equation number 1. Oh, that is just algebra. We will compute for this. So this one will go here. So this is now plus. So the divisor will be what remains. 4.44 F times N, right? This goes up already. So this is now plus. This is involved. That's the mutual flux. In terms of the induced voltage, frequency, and number of turns. Okay? That will be equation number 1. By definition, flux density is flux per unit area. Flux per unit area. If the cross section of the core is this, like this, right? There should be some flux emanating from the core, right? Passing through the core as the current passes through the coil. And the concentration of flux here is termed to as flux density. It's designated by capital letter B, right? So flux density, okay, will be flux, the flux that's produced by the coil in which there was current passing on it, okay, divided by the area. The area is actually the cross section. So if this is 2 inches, and this should be 2 inches, the area should be 4 square inches, something like that, right? So the flux density will be the flux going into the area of the core, okay, divided by the unit area. So this is by definition. Flux density is flux per unit area. If we try to compute for flux density, the designation for flux density is capital letter B with the subscript M. Okay, and this should be, this is Greek letter P, right, with the subscript M, meaning the mutual flux. The flux is the mutual flux, and the area of the cross section of the core is just simply capital letter A. If we try to compute for flux, mutual flux, it should be the flux density times area. We call this equation number 2. Okay, so this is now algebra. Okay, that's why I have a subject matter on algebra. Algebra is very important because when we go to higher mathematics or higher subjects on electrical engineering or other engineering, it's always algebra, right? So we produce equation number 1 and number 2. I place it here, equate equation number 1 and number 2. We are now formulating the equation on how to compute for the value of flux density, right? So if we try to equate the value of the flux density by using equation number 2 is flux density times area, right? And the value of flux density using equation number 1 is actually E times 10 to the 8 over 4.44 frequency times n. If we try to compute for B sub n without the A, we will put A here, right? We remove this one. Okay? Then we try to rearrange. We'll combine E and frequency. It is this. Right? So what remains will be 10 to the 8 over 4.44. Okay? We will take the area. We will take the number of turns. And we equate this to be equal to K1. Why K1? The area of the core, if it's already designed and constructed, it will be constant, right? So it will be A. So this now is constant. And the number of turns, if the transformer is done, the number of turns, you could not vary it anymore. So this is still a constant. So 10 to the 8 all over 4.44 times a constant, the overall product of the numerator will still be constant. So 10 to the 8 over a constant, we call that K1. Right? So what will come out? Flux density now, right, will be E all over frequency times K1. Right? So this E here is variable, frequency is variable. It could change, right? It depends on the power system. If you change the frequency, of course the flux density will change. If you change the induced voltage, of course the flux density will also change. So this what I call this induced voltage and frequency are both variable for the meantime. This is times Q1. Okay? So if we now try to go back to the first equation here, capital letter P with the subscript H, I'm following this. It should be KH times frequency times the computed value of flux density, which is this. So this should be K1 times E over F, all raised to 1.6. It is this. And if we try to simplify this one, okay, this K1 here should be raised to 1.6. And K1 raised to 1.6 will be this. Right? And we combine this with KH. So meaning to say the product of K sub H times the value K1 raised to 1.6, we call that at C1. So this is now C1 times frequency, right? Times the ratio E over F raised to 1.6, and this is in watts. Okay? So the given right hand side is actually under exponential function or equation because the power is 1.6, right? So for any transformer, the hysteresis loss will be a certain constant C sub 1. For the meantime, we do not know the value of this. So when you are given a problem, you must have to compute for this. Okay, C1 times frequency times the ratio E over F. Okay, we take the ratio and we raise that to 1.6 and the unit will be passed. So how many variables are actually controlling the value of this hysteresis loss? There are 3. No, there are 2. It's only the frequency and the induced voltage. Right? We put a simplified formula for hysteresis loss here. If the ratio E over F is constant, if the induced voltage is constant and the frequency is not changing, right? We could say that this ratio here will be constant. So if this will be a constant times C1, it will again be constant. So actually we could say that the factor who will determine the value of the hysteresis loss is just that hysteresis loss is directly proportional to frequency. Okay? If the induced voltage is fixed, right? We could say that the hysteresis loss is directly proportional to the frequency because this will now be constant, right? C1 times C will be a constant. So the remaining factor that will control the value of hysteresis loss on the right hand side is just the frequency. So I place it here. For hysteresis loss, this is directly proportional to the frequency. Oh, this is a topic under college algebra, the variation, okay? PH, capital letter P with the subscript H is directly proportional to frequency. If the ratio E over F is constant. But if it is not constant, right, we'll go back to this equation here. We must have to take the ratio E over F raised to 1.6. Okay, next one. The AD current loss. We will be using this formula here. We'll go back here. Okay. So the AD current loss will be equal to Q sub E, okay, times frequency square, times the value of flux, but this is to the second power, okay? To the second power, that is the ratio. What is flux? It is E over F times Q1 raised to second power. So this is Q1 times E over F to the second power. And if we try to simplify this one, this is square, will be squaring this one here. So this F square here cancel with this. This Q1 here should also be square. So there's a Q1 square here, right? Then we try to combine that Q1 square times K. We call that to be C2. Q1 square times Q sub E, we term that as C2. Another constant, right? So what will come out? Okay, C2 now will be, what remains will just be simply this E square here. So in general, to compute for the eddy current loss for any transformer, it will be a constant C2 times the square of the induced voltage and the unit is watts. So as you can see, the only factor controlling the eddy current loss is actually the induced voltage. But again, if we go back here, if the ratio E over F will be constant, okay, this will become a constant, right? This will become a constant. So we will multiply this one by C, it's again a constant. So what remains is just frequency square. So in general now, AD current loss is directly proportional to the square of the frequency. Okay, you got it? AD current loss is directly proportional to the square of the frequency. For the hysteresis, it is just directly proportional to the frequency, just the frequency alone. But for AD current, it will be directly proportional to the square of the frequency if the ratio E over F on the formula is constant. But if it is not constant, we must have to use this one. Okay? Let's try to bring out the total core loss for any transformer. Capital letter P with the subscript C will be equal to capital letter P with the subscript H plus the capital letter P with the subscript E. This C here refers to core loss, core, this is hysteresis, and this is eddy current. So for any transformer, the total core loss will be the losses due to hysteresis and the losses due to eddy current. So if we try to bring out the formula, we'll take this formula here and this. So the total copper loss now will be C1 times frequency times the ratio E over F raised to 1.6. That's the hysteresis loss. Plus C2 times the square of the voltage. That is for the eddy current loss. And the unit is watts. Okay? So this is exponential. And this is up to the second power. Okay? Where we bring out the legend. Capital letter P with the subscript H is the hysteresis loss in watts. capital letter E with the subscript E is the eddy current loss in watts. Small letter F is frequency in hertz or cycles per second. Capital letter B with the subscript M is flux density, the unit is Maxwell's per square inches. Capital letter A is actually the area or cross-section of the core. In which the windings are born, right? There are laminations like this, right? But if you try to cut it, there is a cross-section, and that cross-section is this one, right? Capital letter N represents the total number of turns, and capital letter P with the subscript C is the total core loss. It is the losses due to the core of the transformer, okay, and which it is the hysteresis and eddy current. And P sub N is actually the mutual flux, and the unit is Maxwell's. Okay, that's it, guys. These are the formulas on how to compute for the total core loss of a transformer. It should be the hysteresis plus eddy current. Okay, this will be the equation. Okay, good evening from Los Angeles. This is Professor Derivation.